Okay, in part two of this now, we're going to connect a load to this transformer that we were looking at in part one. And like I told you, everything's going to break loose, and this thing's going to start looking really complicated. But we're going to walk through it and simplify it and discover what all's going on with this load-connected transformer. Okay, so now we're going to go from this relatively simple, unloaded transformer, infinitely permeable core, at no load, and now we're going to connect a load to it. Oh my, got complicated, didn't it? Look at all that's going on with this. There's a lot going on, and we're going to walk through each event, we're going to call them, that has occurred now that current is flowing through the load, and now there are two flux generation cores at work, and how do they interact with each other? Okay, the first thing that we're going to recognize is that now there is current flowing. I1 is flowing and I2 is flowing. And what we can do, we can go back to our equation that relates current to turns ratio, and it is an inverse relationship, right? And so I1 over I2 equals N2 over N1, inverse relationship in terms of current and turns. We can simplify this, and we can come up with N1 times I1 equals N2 times I2. And we want to recognize that first when looking at this load-connected transformer. Secondly, we want to recognize that there is a magnomotive force created by I2 that's equal to number of turns times the current. There's another magnomotive force or flux that's created from I1 that's equal to N1 times I1. And we want to recognize that these forces are equal and in direct opposition when I1 flows into the polarity mark and I2 flows out of the polarity mark. There was an electrical term called bucking that is occurring, and so we want to recognize that that is occurring, and we've got arrows that show the flux M1 in this direction and M2 in that direction. All right, so that's the second thing we want to recognize. The third thing we want to explore is that the magnomotive force into I2 produces a total AC flux, and we can find that right here. Let me just highlight that, okay? Right there is the total flux that is created from the secondary side, and a portion of that links the primary side. A portion of that is linking that, it's mutual, and then the other part of that, this is the other component of the total flux, okay? And it is not linking, and it's what we call leakage. It's lost, so to speak, and we call that, because it's comes from the secondary side, we call it secondary leakage flux. The fourth thing that we're going to recognize is we're going to put our attention to the primary side, and the total flux that is created on the primary side is here. It is composed of that portion that's linking the secondary, and then it also has a leakage portion which is represented here, okay? So we got the three parts of the primary side, okay? Here's the total, the linked, and the leakage. And we're going to call this primary leakage flux. Okay, so when you look at this, you know, and you break it down into these components, you go, you know what, that's not so really complicated, is it? This is just another representation of the same thing that we're seeing, you know, up here. It's just given to us in two parts. And here's the representation of the portion of the total flux that's linked to the other side, secondary to primary and primary to secondary. And then this is, you know, this is that leakage portion here that doesn't couple because, you know, it's not, we're trying to account for that lack of complete coupling. That's what we're walking through here now. So what we've discovered is now that these two currents are flowing, you know, we have upset this. Okay, and how have we disrupted that with this going on? Well, really, we've kind of already talked about it. First off, the total flux that's created by I1 is composed of the two parts, right? It's composed of this part and that part, and the mutual flux in 10.4 now, this part is not the same as this, okay? So he makes that point. I think that's pretty obvious, but you know, he tells us that. And so that's one portion of it. The secondly, the total flux produced by I2 is composed of this mutual flux and a leakage flux, okay? Third, if we combine, let's go to a different color here. If we combine those two mutual fluxes into a single mutual flux, and we're going to do that here, okay? We're going to call that here, which is the combination of those two mutual flux. The mutual flux is created by the joint action of the primary and secondary, okay? So this is comprised of the two designations here plus here, okay? And so, you know, that's combined into this total mutual flux. Fourthly, we note that the primary leakage flux, this primary leakage flux, this guy, okay, is created by N1 I1, while the secondary leakage flux is created by N2 I2, okay? Consequently, leakage flux, this guy, F1, and this guy, F2, is in phase with I1. I mean, this is in phase with I2, and this is in phase with I1. Okay? And fifth, the voltage E sub S that's induced in the secondary is actually composed of two parts. And those two parts are, remember, anytime you have flux, you're going to generate a voltage. So we can say that that this E sub S total voltage is equal to the portion from the leakage flux here generates a particular voltage that we call this, and then the second component of this, indicated with the plus sign, is this E2, and it's going to be dependent upon this flux, okay? So, you know, composition of two voltages based on two different flux given. And it's interesting to think that both of these are most likely, in general, not in phase, okay? So that adds a complicating layer to it, but you know, we want to recognize that part of it. Okay, we also want to look at the primary side, and we want to understand that E sub P is also composed of two parts, okay? E sub P is also composed of two parts: a voltage that is created because of this leakage flux given here, okay? And that, of course, is that part of it. And then another part, E1, that is created from this flux, that we're now defining as the combination of the two, and it's given as that equation. And again, these two voltages are generally not in phase. And the last, finally, sixth thing that he tells us is that EP, the induced voltage, is equal to the applied voltage. Now, using these 6 basic facts, we got 6 basic facts that we can walk through, and now we can develop an equivalent circuit of the transformer that will allow us to model it as a practical, real-life device. And again, if you need to walk back through to make sure that you understand that, look at this again, walk through the slides. But once we go through it individually, we define all these things, it's really not that complicated, is it? The basic fundamentals apply. It's a little bit busy, and there's a lot going on, but we can pretty easily account for everything there. All right, so we'll call that 10-2 and stop this one at this point.